This video is going to have a look at applying a geometric sequence to a practical application scenario involving decay. When we are looking at decay in geometric sequences, our starting point is the general rule, and that is Tn is equal to T1 times by r to the power of n minus 1, with T1 being the starting term and r being the common ratio, what we are multiplying each term by within the sequence. So we're going to be applying this general rule to be able to model a scenario with decay. So when we are looking at decay scenario questions and we need to be calculating our R value, we're going to calculate it by taking away the decay percentage from 100%. So we're going to end up with an R value of less than 1. Having an R value of less than 1 means that our numbers are going to be decreasing each time we apply that R value, which is what we want, because when it's decaying, our numbers are decreasing. So for example, if we're declining by a rate of 6%, our R value would be 100% minus 6%, which is equal to 94%. Now to use that in our general rule, we're going to need to put that into a decimal, so 0.94. So if we were having a scenario where we were declining at a rate of 6%, the R value would be 0.94. So let's have a look at an example of how do we apply a decay scenario using the geometric sequences. So in the example, the population of wombats at a national park is decreasing by 8% every year. There are currently 830 wombats in a national park. So it wants us to start off by writing down the rule for the number of wombats after n years. So to be able to write down the rule, I need to be able to identify my starting term and then the common ratio. So the starting point is going to be 830, and the common ratio is that it's going to be decreasing by 8% every year. So it's going to be 100% minus 8% because it's decreasing. So 92%, which equals 0.92. So because it's less than 1, I know that my values in my sequence are going to be decreasing every time I multiply by 0.92. So before writing the rule, let's just have a look at what it's going to look like. So I'm starting off 830, and then after 1 year, it's going to be 764. After 2 years, when it decreases by another 8%, it's going to be 703. So I can see that my first value is 764, not 830. So because our starting value of 830 isn't actually part of the sequence, that means we have a T0 value and not a T1 value as our starting point. So we're going to need to factor that into our rule when we are writing it. So let's have a go at writing our rule, and it's going to be Tn is equal to our starting value of 830 times by our common ratio of 0.92. But because we've used a starting value of T0 as opposed to T1, it's going to be to the power of n instead of n minus 1. So we only use n minus 1 when our starting value is T1. Because it's T0, it's just going to be a straight n. So the rule for the number of wombats after n years is going to be Tn is equal to 830 times by 0.92 to the power of n. So now that I have that rule, I can go ahead and look at part B and C of the example. So part B is asking how many wombats are going to be left in the park after 4 years. So what we're going to do is we're going to substitute n is equal to 4 into that equation. So T4 is equal to 830 times by 0.92 to the power of 4. So using the calculator, it's going to equal to a value of 594.61, and that is going to round to 595. So it rounds to 595 because we haven't gone past the 594 value yet, so it stays at 595. So we'll go ahead and write that as our final answer. After 4 years, there are 595 wombats left in the park. So now that we've answered B, we can move on and have a look at part C. So in part C, it wants us to calculate how long it would take for the numbers to halve. So we're going to answer that by substituting in half of 830 as our value of our term. So to calculate that, our Tn value is going to be 830 divided by 2, which equals to 415. So I can substitute in that value into the equation. So 415 equals 830 times by 0.92 to the power of n. To go ahead and start simplifying that to be able to get my n value, I can divide both sides by 830, and that leaves me with a value of 0.5 is equal to 0.92n. So now that I've got that to this point, I can go ahead and start substituting in values for n to see which value is going to get me a value of 0.5. So I'm going to start off with n is equal to 6, so 0.92 to the power of 6 equals 0.606. So it's not that because I'm still a little bit away from 0.5. So I might try n is equal to 8. So 0.92 to the power of 8 is going to equal 0.513. So I'm getting closer, but I haven't gone past it yet. So I'm going to try n is equal to 9 this time. So 0.92 to the power of 9, and that equals 0.472. So I can now see that I've gone past the 0.5 that I was looking for, and that's going to occur after the 8th year, before the end of the 9th year. So during the 9th year, it's when the wombat population is going to halve. So writing out the answer, the wombat population will reach half its current population during the 9th year. So that's an example of how we can use geometric sequences and apply to a practical scenario where we're looking at numbers decreasing or decay.